can raise lots of questions, which was very interesting. And now Laura is going to give her third lecture.
Third lecture, yes. Can you hear me? It's working? Okay, good. So, we ended yesterday giving the pictorial description of how we can imagine to attack the calculation of a collider event. And we already introduced some definitions. We already introduced some ideas of where we can work and where most of our effort is going to go, because we can do things. And we will discuss while we go along why we can estimate the kind of uncertainties that we have at different levels. So just to remind you about the pictures that we had on the blackboard, I don't want to go through the whole discussion again, but I just wanted to have here what we're going to do together today, right? And how we're going to comment about it. Remember that we said, let's have a sort of unique description that puts together both hadron colliders and lepton colliders, and then let's imagine that the lepton collider case is just a simplified version of the picture that we'll have on the blackboard. So I'll draw the complicated picture, and we'll talk mainly about the complicated picture while we go along. But as you will see, at certain points, we can simplify our life, if possible, right? So remember that the picture that we had on the blackboard was just describing the collision of two bound states, so like two protons, like PP, for instance. And I'm saying what I just told you is just this can reduce to a single particle if we are looking at the lepton colliders, out of which we are singling out a hard collision, so a collision that is happening at a transverse energy with respect to the direction of the beams, such that we can observe it out of the mist of everything that is happening along the beam. Plus, in the case of a hadron collider, we don't have to worry about not knowing the initial energy of the collision, because we don't know exactly, as at a lepton collider, what are the energies of the two beams. So let's single out an event. So this will be a parton coming out of one, a parton coming out of the other, and interacting at high energy in what we call the hard scattering. So this is our hard event or hard scattering event, right? And so, as I told you, so this object is a parton, so it can be a quark, an antiquark, or a gluon. Same on the other side. If this momentum of the first parton is P1 and the other is P2, as a matter of fact, that they are equal and opposite, this will come with the fraction x1 of that momentum P1, and that will come with the fraction x2 of the momentum P2. And we discussed yesterday how we can estimate the exact functional form, or we can write the functional form of this density, or partonic density, that is coming into the collision with what we call the parton distribution functions. And remember the color code that I used yesterday was a kind of, I think I had in red the part that we could calculate in perturbative QCD, and the part that we could not calculate in perturbative QCD, so there were non-perturbative effects. So I'm kind of using the same color code today, except that what I told you yesterday is just that, yes, there is a non-perturbative element in here, but there is also a perturbative element in the connection between the parton coming out of the proton, so from the bound state, and the parton entering the hard scattering, which is the evolution of its density from the scale of the bound state, which is about lambda QCD, to the scale of the hard scattering that we quote in general as Q, and is high energy. So this is the high energy part of the story. So the evolution in going from the hard scattering back to the low energy of the bound state is perturbative, and that's why I draw it in red. And you will see this most likely tomorrow, not today. But then I also told you that how out of the hard scattering, we have a component coming out, partons coming out, also leptons sometimes, but let's focus on the QCD part of it. And from here on, however, nature doesn't stop. It's not just that the story ends at the high energy at which we have accelerated the two partons and collided them, but strong interaction keeps working. And they keep, therefore, transforming the original hard partons that are coming out of the collision into weaker and weaker ones, or less and less energetic ones via radiation. So you emit, for instance, a gluon, and this can split into two quarks. You emit another gluon, it can split into two other gluons. And this keep going with the same story over and over and over, till you reach an energy that I think we indicated with the Q0, if we started here at Q, that is again of the order probably of lambda QCD. And so on a time scale, both in this case and in that case, much longer with respect to the time scale of the hard interaction in which hadronization happened. And definitely this is a blue scale. So this is a scale in which non-perturbative strong interaction effects happen. So today we wanted to start looking at what I also told you yesterday, is just in going from here to there is some red history. So in going from here to there, this part here can be sort of calculated perturbatively. So again, the evolution going out can be at least approximately calculated perturbatively, so with perturbative QCD. So remember that red is perturbative QCD, and blue is non-perturbative QCD. So short distance QCD effect, a long distance QCD effect, something that we can calculate with the Lagrangian QCD that you have learned in the standard model, and all the nice properties of asymptotic freedom and weak interaction of strong interaction becoming weak at the high scale that you have learned in your standard model lectures or in your life before this school. And the other is a part on which we have still very little control from first principles, but some control from phenomenological arguments that I will bring to you along the way. So, of course, in this discussion, you can tell me, and I probably already made this comment, but let's make it again. You can tell me, why are you focusing just on QCD? Well, first of all, because if the collider is a hadron collider, this is the most important thing that you want to do in first approximation. Remember that in physics, we always go in layers. We start from the leading effects, and then we go to the sub-leading effects. And that's because if I wanted to add, for instance, QED on it, which is more weakly coupled with respect to strong interaction, even at high energies, I sort of know how to do it once I know how to do QCD, just because it's a simpler version in a way, meaning that, again, it's a radiation of massless particles, because photons like gluons are massless. And so I sort of know how to superimpose in the final state, as well as in the initial state, QED radiation to this story. And as a matter of fact, the parton distribution function these days, they include both QCD and QED evolutions. So both effects are in there. And when we look at parton showers, which I haven't written the word on the blackboard today, but is the part that is the, if you want, the name that we associate to the algorithmic generation of these radiating process that brings the hard parton coming out of the hard scattering to lower energies via QCD radiation. So this algorithmic realization of what the QCD Lagrangian tells you that should happen over and over, these parton showers, the name of which normally is parton shower event generators, right? But this through parton shower algorithm, these days, they do include both QCD and QED radiation. So if you go to the gory details, you see that there is a switch that you can turn on. You can also include the QED radiation, photoradiation, and QD radiation in the shower. Sometimes they're not included at the same orders. Sometimes the orders are sort of not complete, if you want, but it's there. So it's not that I wanted to leave it out of the discussion. It's just that since this is the main effect, once we understand this, we understand that as well. And then you're telling me, what about electroweak interactions? Electroweaks are very different, right? They're very different because, first of all, the gauge bosons are not massless, right? So they're very massive. And so unless you go to extremely high energies, like an FCCHH, for instance, 100 TeV, where also an object of 90 GeV is almost massless, right? Otherwise, they should behave differently, and they should not behave, they cannot be, if you want, embedded in the same formalism, and we should not really treat them as radiation. So when you emit a W or you emit a Z, it's a different process. It's not just dressing up something with the W with the Z. It's a different process altogether. So this object here is a different hard object. We are not including those in the PDF. We're not including those in the shower. We are producing them as massive object in the hard scattering process itself. And then from there on, we evolve whatever is left through the same mechanism. So this is to say that I'm not leaving out things, and I'm not just giving you a corner of the story. So the story is a complete story. I'm just focusing in the discussion that we are having here on the QCD part of the story because it is, as I said, the leading effect, and it teaches us everything we need to know in order to move forward. As to say, if we had to go to the FCCH age, so PP interaction at 100 TeV, we would treat the W and the Z exactly as we treat partons here. So we already know what to do, right? And if not, it's just because they're not partons, right? Okay, so what we wanted to do now is just, therefore, to basically map this picture into a formula that is what we will use in order to calculate rates, which is what we measure at a collider. So cross-sections, but I call them rates in full generality. They can be total rates, they can be differential rates, depending how much inclusive we are on the phase space, depending how much we integrate over the kinematical observables, the kinematical variables that are part of the phase space. So if I map these into a formula, I can say that, and I think I have space enough here, I can say that the cross-section to go from a given initial state that are the initial state of my two protons, let me call them H1 and H2, but it could also be in the simplified version lepton 1 and lepton 2, so hadron 1 and hadron 2, to some final state that for the moment I call just final, and then we'll specify what this final is. So this H1 and H2 could be a proton-proton, could be a proton-antiproton. So for our discussion, let's focus on proton-proton. The L1, L2 can be any plus or minus. And you can take some other leptons if you like, but it doesn't matter for our discussion. So this object will have to be written, or if you want, I can write proportional so that I don't have to worry about the prefactor that comes here in front. Is a flux factor that comes here in front. It's 1/2s, as a matter of fact, but this is not the point of our discussion. So it will be given by integrating a parton level cross-section, which is the cross-section for the red process, the cross-section for this process here, over, of course, convoluted with the distribution of partons that comes from the first proton, and for the second proton with a fraction of the energy momentum of the proton, x1 in one case and x2 in the other case. So in other words, if I associate it to the full process that I've depicted here, a rate sigma, I will associate it to the hard scattering process, the parton level process, a sigma that I call sigma hat, which is just the one that is induced by the two partons and not by the two protons. And the difference between the two is just that this guy, the sigma hat, will have to be, as we say, convoluted over the probability of finding a parton in the first proton with a fraction of the energy x1, and the probability of finding the other parton in the other proton with a fraction of the energy of the proton x2. So if I have to write this in formula, I will write this as the integral over dx1, and of course these fractions goes from 0 to 1, right, of the probability, let's say, of finding a parton, let's call it I, in the first hadron, let's say H1, or I can call it directly P, with the fraction x1 of the momentum of the parton. And let me leave a space here, because I wanted to comment about what other arguments that this object has. And then I will have the integral, and same between 0 and 1 of dx2. And sometimes, depending on the situation, there may be connected boundaries between the two of the function of the probability of finding another parton, let's call it J, in the second hadron with the fraction x2 of the momentum. And let me leave a space here again to put the other argument in it. At this point, since I'm using a generic I and a generic J, depending on the process, I can have more than one possibility. So there can be processes that are induced by a QQ bar, a QQ, a Q bar, Q bar, or they can be induced even by a Q glue or a glue glue. It depends on the process that I have. So I have to leave all the possibilities open, and I will have to sum over them because I obtain the same final state with different possibilities. So let me say that in front of everything here, I will have a sum over I and j. And then at this point, going to the other blackboard, here I will have my sigma hat. So I have the sigma hat of the I and j object going into the final state. And this sigma hat will have arguments as well. Definitely will be a function of x1 and x2, just because the center of mass energy at which this guy lives is obtained from the center of mass energy where the other guy lives, just multiplying it by x1 and x2. So the S hat in which this guy lives is x1 times x2 times S, where S is the center of mass energy at which this guy lives, right? So, and then it can be function of something else that I'm not writing because something is still to come in the arguments of this function. And technically speaking, I'm done up to here, right? So I have calculated everything except the evolution with the Parton shower and except the hadronization. So this is the point where you interface your calculation, you feed your calculation to the shower, the Parton shower event generator. So the Parton shower event generator takes your calculation at the Parton level and it evolves from there. So if you want, you can embed your evolution also in sigma hat, and you can write here something times the Parton shower, which is a super sloppy way of writing. But what it means is just that this is fed into a Parton shower event generator that takes whatever is coming out of the hard scattering with a weight that is precisely the calculation of your cross-section multiplied by the densities that you have here, and it evolves it from there with the criteria and with the algorithm that we will understand today, why it is done the way it is done. So, first of all, these objects that I have now written explicitly in formula on the blackboard, they contain, as I said, a perturbative component. We calculate them in perturbative QCD. What, in particular, do we calculate fully in perturbative QCD is this object here. Or we can calculate it in perturbative standard model in general. So we use the standard model, including QCD, including QED, including electroweak if it's needed, to calculate this object here. So this object here is really full red, right? Now, since you know the standard model is a renormalizable model, we have no problem in calculating finite objects, so in calculating this sigma hat as a finite quantity. We know that upon renormalization, of course, all the different parameters of the model, masses and couplings, become running objects that depend from what we call the renormalization scale. And so there will be a renormalization scale dependence in this object because it's not calculated at all objects. It's calculated up to a certain order. So when you see calculations that are done at leading order, next to leading order, next to leading order, and etc., it means that to start with, this object here is calculated at that order of whatever interactions they refer to. If it's QCD, it's QCD. If it's QCD plus electroweak, it's QCD plus electroweak. And when you say electroweak, we include also QED, right? So it's the full electroweak part of the story. So here in the empty space that I have here, I will have to put, I'm going to put a mu sub r, which is the renormalization scale that is technically a non-physical scale from which my cross-section depends because it's not the full thing. We have a perturbative approach to the calculation because we haven't solved the QCD, right? So that's the one of the, if you want, limitations that we have, but also because we know what the dependence on mu r is at all different orders is also what allows us to determine what is the kind of uncertainty that we have because of that dependence. It's not a random dependence. It's a dependence that we know where it comes from. Now, what about the F1 and F2? So the F of the Parton I in H1 and the F of Parton J in H2, well, they also depend on mu r Many times this is not written explicitly, but they also depend on μr, that often is identified with another scale that I'm going to mention soon, because they're also calculated perturbatively, not so the way these objects are calculated, as we will see tomorrow, is from a non-perturbative core, which is actually what lives at the scale of the bound state and that we fit from experiments, we fit from data. We evolve from there on with QCD at increasing perturbative orders. So in the calculation of these objects that have to be matched to the same order at which I have calculated the sigma hat, we will also apply the renormalization of QED. And if we have PDFs that also include QED, we also apply the renormalization of QED. So there is a μr dependence in these objects as well. So in this object, I will also have a μr dependence. And then finally, there is what is called the dependence on a scale that is called the factorization scale. And this is a very important point. That is, of course, present in all these elements of the equation. That is really the scale at which we match the parton density to the hard scattering. And this scale is as arbitrary as the μr, and is typically a scale that since all these dependencies that we have inside are dependencies of a perturbative expansion, they're typically studied in such a way that the behavior, the converging behavior of the perturbative expansion that we are considering is optimal. So moving this scale, you can shift large corrections around from one to the other, and you typically would like to shift to the ones in which they have a least effect, or to the ones that you can calculate more easily or a sum. And this is a discussion that we can have later. For the moment, let's focus on what we are doing. So this is really the big picture of the story. And so as I have mentioned here, there is definitely a red part in these objects. I'm not saying that it's completely so, because in each one of them, there is what I would call an F sub 0, which is a non-perturbative core, which is where I start is the boundary condition, if you want, of my evolution from the scale of lambda QCD to the scale of the hard process. While there is nothing that is non-perturbative in this part here, there will be some non-perturbative match by the time I have evolved from the hard scattering to the scale of hadronization, but all towards the end. Everything else that is in here is perturbative, basically. Okay, so so what we are going to do and to see, right, to calculate, are really these 3 steps, or 2 steps, if you want, or probably three components, right? So we have a sigma hat here in the center. We have PDFs on this side, or if you want, we have if you want initial state. H1, H2 on this side, and we are evolving here with the pattern distribution functions. And today we will mainly see the other part, and we are then evolving here to final state. Hadrons plus leptons with parton showers. So this is purely perturbative QCD, and these other two have a QCD component, the perturbative QCD component. Now, what we're going to see today is just that because you go from here to there using QCD evolution, and from here to there using QCD evolution, it is really important to study what that means. So it is really important to study this core and to study what is the nature of QCD radiation. So what is this what is the structure, what the Lagrangian of QCD and the property of QCD tells us about what is the structure of the radiation that a strongly interacting object emits. Because once we understand that, we understand really the structure of an event. Is that a question? Okay. Sorry, I couldn't. Well, not a, it, yeah, so it's, we have different regimes, energy regimes in this process. So whenever you are in a high energy regime, you know that QCD is weakly coupled. So you can use perturbative QCD. And this is what applies definitely here. And this is what applies to the evolution of the parton density, as well as to evolution of the radiation coming out of the Hart scattering till the energy is not so degenerate or so decreased that you are entering a non-perturbative regime. Now, when that happens, it's a matter of hand waving. But we have a scale, the scale of lambda QCD, where the coupling becomes large enough that we couldn't justify a perturbative expansion anymore. So we take the hadronization scale, the scale of the PDF course to be of that order of magnitude. Does that? Well, at that point, the thing is what I was referring to. In one case, you have some non-perturbative core. That is your boundary condition, if you want, for the evolution of the PDFs. And this is you fit from data. You cannot calculate it. Unless you have, OK, you should have a first principle, the possibility of calculating it first principle. And that can come only from something like lattice QCD, for instance. Lattice QCD could do that. There are, these days, the first attempts to the calculation of parton distribution function with lattice QCD. They're pretty good compared to 10 years ago. I mean, it's incredible progress. But for what we will use here, what you can use today, all the different sets of PDFs that we are used to link to our calculations, they have all been calculated from a non-perturbative core that is fitted from data. And the same appears here. So here we will calculate the pattern of QCD radiation. And at the center point, we will have some hadronization algorithm, right, that proposes a certain matches between parton and hadrons. And of course, we don't do it at random. So we don't do it just say, oh, must be like this. We again, test it against the data. And so one thing that you look, for instance, is just you estimate the density of certain partons. You can calculate, for instance, the density of gluons in your radiation. And then you match that to the density of hadrons. And you see that is a common rescaling factor. So things like that, right? So, OK. So where we were just saying, this is the really important object that we wanted to calculate because we wanted to see we want to study what are the properties of QCD radiation. And we will use that both to build the radiation backward and to build the radiation forward. So what we look today will be mainly the radiation forward. And tomorrow, when we are going to talk about parton distribution function and see how we control them, we will talk about the radiation backward. The difference between the two, you say, but maybe the same thing, right? Well, yes and no, because the difference is clearly radiating particles. So you change the energy of what goes, of whatever radiates. And in this case, there are two objects that are coming into the collision. So changes their energy, changes the center of mass that is coming, the energy in the center of mass that is coming to the Hart scattering. While in this case, the scattering has happened already. So little matters. You don't change the properties of the scattering because you start radiating. But in this case, you change the properties of the scattering in terms of the energy that is going into the scattering because of radiation. So that is the main difference between the two, to the point that certain matching that we will see today doesn't happen in the initial state, but it happens in the final state. So that's why we distinguish between the two. So being interested in controlling the evolution of the radiation, of QCD radiation, and how that tells us, what that tells us about the shape of events at collide and how we can model them, we will look at the process and focus on the final state radiation of that process, the final state QCD radiation of that process. So we are looking at sigma hat, right? So first of all, looking at this one. So now I like to use this blackboard, so let me take this part away and work around what we have here. So I want to keep these. Of course, to be really complete, I should say in writing these, we're leaving out so effects that I will comment about right now. So this is just telling us, and you could question about that, that I can describe this complicated messy process like product of things. This is the essence of the factorization theorem of QCD. So it factorizes the short distance from the long distance part. And it factorizes it both in this way and even in the factorization with respect to the radiation that comes after. Those effects are there. We are not dropping them completely. It's what goes into the PDFs and what goes into the hadronization process, but are effects that are of the order of lambda QCD over the scale of the process to some power. And one of the big efforts, or one effort, is really to quantify these. And there is no universal answer to that so far, but there are cases in which these effects have been studied and shown to be negligible for certain processes. There is no universal statement here. With respect to negligible, of course, relative to the level of precision that we can get, to the level of the systematic error that we have on the rest. So focusing now on sigma hat. Sigma hat is calculated perturbatively, right? So it's a perturbative object. And as such, it can be calculated as an expansion in the couplings that we have. So it can be calculated, if we're talking about QCD, as an expansion in alpha S, or it can be calculated as an expansion in alpha S and the other couplings of the standard model. So let's therefore think of sigma hat in general as an object, and let's remind ourselves what are the ingredients of calculating sigma hat. So you may have seen, I'm sure that if you have taken a class in QFT, you have for sure seen this formula before. And let's remind it to us. So if I write a sigma hat that here is written as the sigma hat for an initial state ij going into a given final state, depending on x1 and x2, because this is what gives me the center of mass energy of this process, and depending on the renormalization scale. But let me write it now in terms of the momenta that are coming into play. So if I have an object, let's say this is the momentum pi, and this is the momentum pj of my two objects, I and j over here. Let me switch, since I'm going to use I. I don't need to use I necessarily, but I will have a set of final state momenta that let me call it pk, for k going from 1 to n. So I have two momenta in the initial state given to a set of n momenta in the final state. This is a 2 to n process where n is generic. Can be a 2 to 1, can be a 2 to 2, can be a 2 to 3, can be a 2 to n, a generic process. So the formula that I'm going to write now is the one that you know very well. So if this it's a total cross-section, I would have an integral on the other side. So not to write this integral, let me write it as a differential cross-section. So here you have the differential that is the differential of the phase space of the object that you have in the final state. So I will have a product for k going from 1 to n of the phase space of each one of them, which is a d3pk divided 2 pi cube and 2 the energy of these particles, E sub k. And this is the phase space. Let me not use PS as Parton shower. Let me write it explicitly. The phase space measure, right? Which is incidentally also Lorentz invariant. So we are writing all Lorentz invariant things. In front of here, you have a normalization factor that is typically 1 over 2, the center of mass energy, that in this case will be the center of mass energy of this process. So it will be the S hat. If it had to be, this process had to be a lepton-lepton process, all the S hat will go away. They become S. And there will be no densities on anything. So it will be much simpler. The S hat is the S. Sorry, the sigma hat is the sigma, right? And then here we have, if you remember, there is a factor that just expresses the conservation of energy and momentum. So pi plus pj minus the sum over k from 1 to n of pk. And then the important element that you have here is the scattering amplitude for this process that I think we called with the letter A previously of pi pj going into the set of momenta pk square. So this is the object that we wanted to calculate. So let's pause for a second. This is the formula that most likely you have seen, right? And it's a formula that It's universally valid in calculating the sigma hat. It can be, it's very simple to write, it's very intuitive. So this is your probability for the process to happen, calculated quantum mechanically in quantum field theory. This is just conservation of energy and momentum. This is the integral over the phase space. You integrate completely, you get the full cross-section, the total cross-section. You integrate partially over the final state space, you get different kinds of distributions. Now, this, I'm sure that you have worked out by hand many times, probably, the 2-to-2 case. The 2-to-1 case is trivial. So if you work out the 2-to-1 case, you just guess that the one particle produced has a fixed energy that is just equal to the S available in the center of mass. The 2-to-2 is also very simple. So the 2-to-2 is just, if you count how many degrees of freedom you have 3 degrees of freedom per particle, so you have 6 for a 2-to-2, you take away 4, you have 2 integration variables in your phase space, and you keep going, right? Now, do we do this by hand? Normally, the 2-to-2 case, yes, because it's something that you learn and you want to see if you have understood what is happening and how to do these things. The 2-to-3 is still manageable. However, once you have understood what gets into that calculation, you don't want to do it by hand, and definitely from there on, you don't want to do it by hand, and not even if you are really interested in a full inclusive cross-section. And what I'm alluding here to is just that most often, it's true that we calculate a given process, but we typically calculate that process, if we want to compare with experiments, limiting the phase space of the final state by different constraints. There can be cuts on the energies, there can be cuts on the angles, and if you try to calculate that by hand, it's a nightmare, right? Not only, but you have to recalculate everything every time a new cut is proposed, right? So you normally do this part of the integration just via Monte Carlo. So you do it numerically, just changing your variables of integration with a change of variable to random number that you then integrate via Monte Carlo, and very easily can implement with a few lines of code any cut that you want on the integration variables that are angle and momentum, or angles and energy, or whatever you decided to use. This done. Now, there is some interest in looking at some of the regions of this integration, which is what we will do today. In particular, we will focus in evaluating the part of this integration for the radiation, for the QCD radiation, that is useful to do, that is needed for us to do, because as we'll see, this part of the story, so the amplitude, contains some peculiarities, contains some divergences that we need to make sense of, that are divergences that we call infrared divergences. So let's come, therefore, to the discussion of this part of the story. This part of the story is the probability amplitude square, so the probability, so the scattering amplitude square for the process of 2 particles going to n particles. It's a perturbative object, so this is the one that we calculate in sigma hat at higher and higher orders, so the perturbative expansion in the couplings of the standard model. So this object here, first of all, is calculated as the sum over a generic n that can go from 0 to infinity of, I'm using the alpha of QCD, I'm using alpha s, but it can be other couplings as well, alpha s to the n times the corresponding, if you want, well, this is the, I can write it also for this object, sorry, why not? So, or alpha s to the n, some a, let's call it n. And this can start without the QCD interaction and add the QCD correction later on. Of course, this will be something that then goes into the calculation of the cross-section, it gets square, and et cetera, et cetera. Now, this object here will have, therefore, to be calculated with some, with the theory that you have. So in the calculation, and in the calculation of the cross-section, this object will have both UV divergences, and as we say, they will have divergences that we call infrared. And we will focus on this one, because these are the really, if you want, more physical divergences that we have to discuss. This part is completely taken care of by the fact that you're using a renormalized theory, so it's completely care of by renormalization. So we don't worry about this part, but we focus on the part that, on the other hand, is directly related to the structure of QCD radiation and of even QED radiation that we are considering in our discussion. So what do we have to calculate here? So as we said, I wanted to focus today in building the structure of the final state radiation. So the radiation that goes from the hard scattering process to on, and see which kind of shape those events mostly have, right? So one more comment that I wanted to make about this, also because it's something that I wanted you to somehow to go back and think about, is the fact that this object here, so if you look at this formula, there is a part of this formula that is for any 2-to-n process. But if you have to say where are the characteristics of the process that we are considering nested, where are they? They are in the amplitude, of course. So the amplitude is what makes the difference between process X and process Y. So because here you have all the characteristics of the particles that are involved, if they're fermions, if they're scalar, if they're vectors, et cetera, et cetera. If they're colored, if they're not colored, if they are charged, if they're not charged, it's all in here. And the little very simple problem that I'm proposing to you is just to calculate, to warm up in remembering how this formula goes, for as simple as it is and for as standard as it is, into calculating something as simple as E plus E minus to mu plus mu minus, which is in all textbooks. So you can easily calculate it. You don't need your laptop. You don't need anything, right? So you just write down the amplitude for this process, take the amplitude square, calculating a 2-to-2 phase space, and without integrating till the end, just look at the distribution over. So as we just mentioned, this is a 2-to-2 process. So you have 2 integration variables left. One is the energy, another is or a momentum, depending on what you choose, and the other is an angle, which is the scattering angle between, here is a 2-to-2 process that you can calculate in the center of mass of this object. So there will be one of your kinematic variables that is really the scattering angle for this process. So if you calculate, just try to get to the differential distribution, d sigma d cos theta. So that differential distribution, if I'm not mistaken, has a form like this one, is 1 over 32 pi S, where S is P1 plus P2 square, so it's the center of mass energy. Then you have a phase space factor that is a sort of velocity factor that is 1 minus 4 mu square divided S. And then after that comes the true amplitude square. That I have omitted to say, but in calculating this object, unless you wanted to calculate, you want to keep track of the degrees of the quantum numbers of the object that you are producing, you typically average over the initial state one and the sum over the final state one. And I will indicate that process just with a bar over it. So here we are summing over the spins of this object in the final state, and we are averaging over the spin of this object in the initial state. So once you have calculated that, so you once you calculated this amplitude here, you get a final result that in the normal case of E plus E minus into mu plus mu minus for the muons, the objects that we think they are, and we know they are, you get something that is of the following form. You get a pi alpha square. Notice that here there is no alpha because I factored out only the parts that do not pertain to the amplitude. The couplings are in the amplitude, right? Now I'm taking everything out. So you get a pi alpha square divided for S, 2S, sorry, then multiply 1 plus the cosine square of theta. Really, it's something that with patience and not much effort, you can calculate through, and I say, oh, I got it. And if you find something different, let me know, because probably I have a factor wrong. But the point here that I wanted to make is just a very simple, very silly point, if you want. It's just, if you now imagine that your muons are not fermions, but they are scalars, right? So they don't, something changes, right? It changes because the interaction between the two can still be proportional to charge, but when you sum over the spins, something changes here. So what, if you now, your muons, instead of being a fermion, it's a scalar, then the same expression changes here. So this is the fermion case, and what you will have here is a difference at the level of the scalar case. And what you obtain here is something that coupling-wise is the same. I think there is a factor of 4 instead of 2 here, but the big difference is the dependence of the angle. So the angle now becomes a sine squared theta, right, instead of 1 plus cosine squared theta. And so you immediately see, so this is just a very naive way, or very simple way to convey to you the message and make you remembering the fact that all the physics of the problem is really in here. So this is what brings in the difference between particles. These particles can have the same mass, can have the same momentum, can have everything. This part will stay the same, right? The center of mass can be the same, the phase space factor is the same, but this part changes, and it changes pretty drastically, because if you look at the properties of this distribution behaves very differently over in an interval between 0 and pi. Right? So when you go in an interval between 0 and pi, this object here is 0 at the extreme. This object here is 2 at the extreme. Right? So you go from something that, if I had to draw it, with no units, no anything, but in one case it goes like this, and in the other case it goes like this. Right? And probably here I should put my 0 down here, right? In order. So you can really tell what you have by calculating by the distribution properties of these objects. So the calculation of the amplitude has this physics in it that is very important. Because it has a lot of physics in it, as we will see, is also what is going to tell us really what kind of shape, as here, we see that the angular distribution is very different and is coming from here. The amplitude square in the case of a QCD process or a generic collider process is going to tell us exactly what the shape of the outcoming objects we expect to have. So this was just to explain to you why you see this little thing in the notes that I'm going to post, and how this is related at all to our discussion, to the discussion that we are having here. Nothing to do, strictly speaking, but conceptually, it's just to have you experiencing hands-on or reminding to you hands-on why this is important. So what I want to do now, as I was getting to before this little digression, is just to take a hard scattering process and now analyze what happens to this part of the story, so to the amplitude square, of course, then integrated over phase space, when we start exploring the shape of the QCD radiation of the process. Since we are looking at the final state of QCD radiation, I don't care about the initial state. So I'm taking a process that does not have partons in the initial state, so any plus or minus process, because I'm looking at the final state radiation. So I'm going to consider a process that is E plus E minus to QQ bar. Now, how this happens? Well, these are leptons, these are hadrons, cannot be any gluons in between, so it is a photon or a Z that goes in between. So in particular, I'm going to look at the case. So this process here can happen via a virtual photon or a virtual Z boson going into quark anti-quark, right? Now, unless you are at the Z resonance, clearly the photon is the dominating contribution. And in general, they don't talk to each other, right? So for the purpose of what we're going to discuss here, I'll just stay away from the resonance of the Z boson in such a way that I don't have to worry about how to write that propagator. We'll discuss that at a different point. And I'm just looking at this process here, right? So what this process here is just this. Right? And what we are going to, what I wanted to discuss is if this is my scattering process, so the E plus and E minus, like they're taking the place of the protons, because I say I'm not looking at the initial state, so I'm simplifying my life in the initial state. And the QQ bar are the two objects coming out from there. I wanted to look at what is the shape, if the two Q and Q bar that are coming out from there starts radiating, what is the shape of that radiation? So are radiating them uniformly all over the place, or there are preferential directions in which that radiation is going to come out? That is the question that we have in the back of our mind that we want to answer. It will take a few steps, but that is what is in the back of our mind. So we want to study the shape of that radiation. So because we are doing that, clearly the initial state is completely inert, right? Because they're leptons. So I can even just say, this is what I'm going to focus on, and that's it. So the real process that we will be looking at is the process in which a virtual photon gamma star is going into these two objects, Q and Q bar. That is the process that we wanted to focus on. And more in general, as you will see, this will just be equivalent to saying this is just anything over here with a Q and a Q bar lag coming out. And even at the end of our whole discussion, it will be just saying what happens when I consider the radiation out of a of a hard parton coming out of any process that is before it. So let's focus, therefore, on this gamma star going into QQ bar, right? And let's try to see what is, therefore, my goal is just to calculate from the discussion that we are having here, the sigma of, or d sigma of E plus E minus going into QQ bar via a photon. Now, and I wanted to do that by including QCD radiation, so I wanted to calculate these, since it started order 0 in alpha S, I want to calculate these at order alpha S, right? So I wanted to calculate these at order alpha S. Now, let's start first of all in terms of contributions. What do we expect the contributions to be at order alpha S, right? So the contribution that we expect at order alpha S are of two different kinds. And here is the first, if you want, we need to stop for a second and think about the meaning of what we are doing. So the two contributions that we will have to consider are one, pretty natural, which is just dress this process with a gluon without changing the final state, right? So we will have a contribution, if this is my photon, that goes like this, right? I put in red the QCD part. Now, depending on your choice of gauge, depending on the choice that you do in your calculation, you may have also correction to the external legs. So depending on what you're doing, I put here in parentheses because depending on your renormalization, also choice of the external legs, so how you decided to renormalize the external legs, the quark external legs, you may have, or in which kind of renormalization subtraction you decided to adopt, you may have a contribution from these objects or not. That doesn't mean that they're not there, and I'm really bad at drawing on such a small scale, but these are springy lines, right? So you may or may not have them. That doesn't mean that they're not there. It means that sometimes parts of these corrections are shifted into there and vice versa, depending on your convention, right? So let's say you have what you call the virtual correction. Now, are these order alpha S? Yes, they are order alpha S. Of course, you have to be careful because if you think to the expansion of the amplitude that we have written over here, now these, if I now translate what I'm doing in this term, here we are considering the first two terms in the expansion. So we are considering for the process at hand, so for, if I have to write my A virtual, there will be two terms. One that is a term that I would call alpha 0 in that notation, in which n is equal to 0, there is no alpha. It is what we call the tree-level term. So these correspond to that. And then there will be a term that in that notation I will call alpha S A1, which is precisely the diagram that I have written there on the blackboard. So these are, this part here is the A1. Now, when I input these into the amplitude square that goes into the cross-section, so when I do a virtual square, of course, technically I have 3 terms, but at order alpha s I have only 2, right? So I have a term that will be the 3-level square. I have a term that is the interference between the 3-level and the 1 loop that is made of these 2 pieces. Or if you want, you can write it as 2 times the real part of A0 star A1 or A1 A0 star A1, right? And then I have another term that is the A1 square that, however, I'm not writing because it's order alpha s square, right? So this one would be the A1 square with would have an alpha s square here in front, and therefore I'm dropping at the first order on which we're writing. So you say done. But technically, you're not done. And you're not done if you thought you were done. As soon as you went and calculated this object, you will see that you run into problems. And you run into problems because, as we will see just by looking at the form of this object without calculating it to the very end, but taking certain limits of the expression for this object, you will have divergences. You have infrared divergences that are divergences when the energy and the angular parametrization of these objects that are exchanged here, that can have a broad spectrum of possibilities, go into certain regions that are either the soft or collinear regions of that object. And so clearly, it's an indication that something is missing from the story. And what is missing from the story is precisely the part associated to the real radiation. So what is missing from the story is the fact that when you start considering higher order in the coupling, in the QCD coupling, think to the process that you're looking at. So if this process, and how this process talk to the process that is E plus E minus or photon going into QQ bar plus a gluon. This will correspond to these 2 different processes here, in which an extra gluon is emitted either from the Q, or the Q bar. These 2 processes here. Now, you can say, well, this is a different process. First of all, notice that the sum of these 2 amplitudes that we call real, because they represent a real emission, the emission of a physical gluon, of a real gluon, not a virtual gluon. Well, first of all, the amplitude square, so I'm not, the amplitude technically in powers of alpha s, that is a GS only, so it's an alpha s to the 1/2. But the moment in which I calculate the A real square, this is clearly of order alpha s, right? So it's the same order as this object here. So at the level of the cross-section, these 2 processes come in at the same order. You can still say, well, this process technically is different from that one, so why am I considering it? Well, there is a part of it that is intimately connected to this one, and is the part in which this gluon is degenerate. So this gluon has either an energy so soft, so an energy going to 0, or it's emitted at an angle that is becoming more and more collinear with one of the 2 partons, so the 2 original hard partons, to the point that it coincides to them. So if you want, there is a physical and also mathematical argument to that sometimes are kind of confused one with the other. So because clearly there is physically in the experiment the impossibility of seeing something that is too soft, that will not be necessarily the parton, it will be the spray of object that comes with that parton, but that is so soft that you cannot distinguish it from the original Q and Q bar. If you thought that this discussion done for QED, in which an electron is an electron and a photon is a photon, the argument is exactly the same. So you cannot distinguish a photon if it's coming out too collinear with an electron. But, and you cannot distinguish it if it's too soft. So if it has an energy that doesn't deposit energy enough in your detector to be detected. But that seems to be a sort of practical argument. So an argument of saying we cannot see that because our detector is not good enough. At the same time, there is a mathematical limit, which is really the behavior of this part of the cross-section. When you literally take the limit for the energy going exactly to 0 and the angle going exactly to 0. And at that point, the two spaces, the two physical spaces become the same. So the two objects, the phase space of the ones and the phase space of the other become exactly the same. So they have to talk to each other. They are part of the same process. And if you think it through even more broadly, and that is the reason why yesterday I had written on the blackboard this final state as an f plus x, is really that even when we focus on a specific f final state, what you see in nature, what you see in your detector, what you see in an LHC event is, yes, what you're looking for, but everything else as well. And what you're looking for is not necessarily what is there, but what you are searching in what is there. I'll give you an example. So if we are, suppose you're looking for the Higgs. So the dominant process in the dominant channel through which the Higgs is produced is gluon-gluon going to Higgs. So if you want proton-proton going to Higgs. This is the dominant process. Now, the three-level channel that is producing this object is this one. Now, is this the end of the story? Now, clearly it's not the end of the story, because if this were the end of the story, first of all, these Higgs would not even have a transverse momentum, right? So these Higgs would be just, would have a 0 transverse momentum, while you measure the transverse momentum of the Higgs, right? It's, you open a paper on this, and there is a PT distribution of the Higgs. So where is that coming from? Is it coming from the fact that this is not the end of the story? This is not the only thing that is happening in nature. Nature has this, plus tons of other stuff, including QCD radiation in particular, that is, of course, moving the PT of the Higgs from 0, because now in the transverse direction, there is the PT of the Higgs, but there is the PT of everything else that is there, and so the PT of the Higgs is now 0, right? So, and now, the fact that you're looking for a Higgs doesn't mean that there is nothing else there. It's just that the only thing that your measurement does is just making sure that there is a Higgs. So you're looking for at least a Higgs. But you could be looking for other things. You could be looking for a Higgs plus 1 jet, or a Higgs plus 2 jet. And then you would extend your spectrum even further and still have an X here, because there is something else. So the fact that what you really have to do in calculating this process, that is E plus E minus to QQ bar, is to put into your calculation both virtual and real radiation at the order at which you wanted to calculate it. Now, there is a part of that radiation, the one that really talk to the infrared phase space, if you want, or the infrared integration space, in this case, of the virtual cross-section, that is truly to be added to it. And there is a part of the phase space of the extra gluon that is hard and is there, and you can include it into the calculation of your cross-section or not, depending on how inclusive or exclusive you want it to be. You can have a measurement that say, I don't care about the X that is there, fine, and that is including it, so it's an inclusive calculation. Or you may say, no, I want to see just this Q and this Q bar, that means 2 jets, and nothing else. And then it becomes exclusive, so you will exclude through cuts and through everything else what is there. But in first principles, to start with, you calculate it, okay? So these are discussed. Let's go back to what we wanted to do, which is precisely what is here on the blackboard, right? So we wanted, therefore, to calculate both of these objects and see where they talk to each other. And in particular, we wanted to see and to learn something about the shape of these, what we can say about the form of this part of the story. By the time we have calculated both layers, and we have made sure that there are no oddities left, so there are no infinities left in our calculation for which it doesn't have physical meaning. By the time we have a physical object, we will really wanted to see what the dominant region of phase space of our finite calculation is, because that is what will tell us once you come back here and your Q and Q bar are two of these lines coming out, where are they emitted? Are they emitting all over the place? or are they emitting in certain particular regions? That's what we wanted to do. So let's see what we can do with that. So starting from, I want to leave these on. So starting from the virtual part, what we wanted to calculate is this object here, right? So we wanted to calculate A1. So this is what will give us A1. This, so let's work into the situation in which these two diagrams are not don't have to be calculated, which is indeed the case in which, in particular, this object is a massless object. And let's focus on that one. So you have to trust me on that, right? That this is really what I have to calculate. So let's do first the virtual part. So let me draw a line here and work on the virtual part first. So let me work on that object there. And I think it's worth, for once, to go through the calculation that you have here. So this is the P1 plus P2 coming in of the gluon, sorry, yes, of the photon, sorry. So this is our gamma star. And let's parameterize this diagram with the momenta that are needed. So there is a P1 going out here. I'm going to call K the loop momentum going in here. I'm going to call P1 plus K the one that is coming into this propagator, such that P1 goes out and K comes down this way. If P2 is the momentum going out from the other leg, so the leg of the anti-quark, the P2 minus K is the momentum here. So these are, I've just parameterized all the momenta. We need to calculate this little loop. So it's not a big deal, right? So trust me. So, and therefore I needed to have parameterized all the propagators that are going in here. So this object here will come out, will be calculated as a loop integral. So it's an integral over the loop momentum that for the moment I write as a d for k over 2 pi to the fourth, but that we know that if we have any problem here, we will have to somehow shift this dimension to d, where d is 4 minus 2 epsilon. And as we will see, this is something that we do both for ultraviolet, but also for infrared. And sometimes we make this explicit by putting a little IR into here, saying that these are infrared divergences and not ultraviolet divergences. And then here I'm not particularly interested in looking at the full structure of these objects, so let me not be explicit about the numerator. Let me say that the numerator is a function of P1, P2, and K. And we are not going to calculate it, because what I'm really interested in is the denominator, which is K squared. Everything is massless here. So I just have 3 pieces, a K squared for this propagator, a P1 plus K squared for that one, and a P2 minus K squared for the third one. Now, this is as much as we're going to calculate, nothing more than this. Now we're taking limits. So now we are going to see where the infrared problems is, or are, because there are 2 in this expression. So in order to look at the infrared problem, let's first of all look at what is called the soft limit. So K can be integrated over the entire phase space. In particular, it can be soft, right? So if I write a K for vector as, let's say, having an energy omega K and a 3 momentum K, and this is a massless object, so the magnitude of this momentum K is also omega K, and I take in the soft limit, well, this gives me an omega K square. This object here, think of P1 plus K square, is a P1 square, which is 0. It's because they're massless. Is a P1 dot K, and is a K square. And again, if I'm taking a soft limit, this is the leading term, because this is a square with respect to this that is linear. So in the soft limit, this guy here behave as an omega squared to the fourth. There is an omega square here, an omega square, an omega here, and an omega there. And then I have the P1 plus K. So I have the 2, if you want, I would have to write these as the leading pieces in here. So first of all, this goes to K squared 2p1.k, 2p2.k, with a minus sign, but as I didn't specify the numerator, I'm not also particularly interested in the minus sign. And so this will have a behavior that goes like omega k to the fourth. And then we would have 1 plus 1 minus the cosine of the angle between k and p1, and 1 minus the cosine of the angle between k and p2. Let me indicate them this way. So it's the angle that enters between P1 and K and the angle that enters between P2 and K. So you immediately see that this object has two kinds of divergences. A divergence that is induced by the limit in which omega k goes to 0, which is this one. So you have a divergence that is the one in which omega k goes to 0, and you have another kinds of divergences that are the one in which the cosine theta of kp1 and the cosine theta of kp2 go to 1, which corresponded to the angle theta kp1 and the angle theta kp2 going to 0. So this globally we call infrared divergences, although infrared normally suggests something with a small energy. So very often you find denoted as infrared divergences only the first kind. I like to call them all infrared because they enter in this discussion of the radiation. And the first one, I would call it soft, because it's really when the energy becomes small. And the other one, I would call it collinear, because it's when the angle between momenta that here are virtual momenta, they're not really the real angles, but they're just integration variables, if you want, become small. So if you had so what you have to do at this point, this is the point in which if you had ignored anything else, you would have to stop and say, what do I do? Because yes, you can regularize them as you regularize UV divergences, but there is no counterterm to take them away. Right? So there is no physical anything that you can define in terms of which you re-express the parameters of your theory in such a way to reabsorb these divergences. So you would have a problem till you realize that you're missing something, so that you're missing this part of the story. In fact, if you had to carry through the calculation till the end, you re-express your well, you're not going to do it here, but you rewrite your d4k over 2 4 pi as a ddk over 2 pi to the d. You work out your d-dimensional phase space, and you will see that you get expression the final integration will have integration in d omega k over omega k. I'm rewriting the ddk in this way, and it will have integration in angle or cosine of the angle over the angle itself. So at the end, you would have integration that in the small angle limit will look like this. So you will have double divergences or single divergences depending on what the limit of integrations are here. So if you had from here to carry through and get to the calculation, let me write it here because I want to use that for the real part. If you have to carry through the integration, here I'm not doing it. I'm just telling you in the infrared limit. That means both soft and collinear. What you would get for sigma virtual is something that has sorry, that first of all, so this is the sigma that factor out the lowest order. So let me call it sigma 0. This is the tree level. And you will have a factor of alpha s because we are calculating alpha s correction. And then it will start with two terms that have one, a double divergence, and the second one, a single divergence, and then a bunch of finite terms. So this is what you will see if you carry out the calculation till the end. So you will see that the divergent part that has infrared divergences, it's order alpha s, and it factors out the lowest order, and is of this form. It has a double pole in dimensional regularization that correspond to the double divergence that we see here. It would also have a single pole with only one of these two regions. So the other one is fine, and the theta goes to 0, or the omega goes to 0, but the theta doesn't. And then it has everything else that is not divergent, that goes both with the finite remainders of this integration and with the part that we have not considered, because here we have taken a soft limit, right? So we are working a soft and collinear limit, right? So everything else that is tedious and complicated in this calculation, as you have seen, isolating the divergent part is normally very easy, and it is very simple, and you can do it even on a piece of paper. Calculating everything else that goes into this final part, which is actually what you need at the end of the story to really have a physical number, is not what we wanted to discuss here. But it's there, nevertheless. Now, let's look at what happens on the real side. So we now wanted to look at the real radiation. Well, if we look at the real radiation, we have those two diagrams. So how can we simplify our calculation? We can simplify our calculation if we look a little bit more closely to the structure of these two diagrams that I wanted to analyze with you. Just because at least once it's an interesting, it gives a little bit more substance to the result. So again, let's work out what are the momenta that we have here. So this is our process. So this is the outgoing quark. This is my gluon going out with momentum k. Let me attach a polarization epsilon to it. Let me give Lorentz index mu to the photon that is coming in with momentum q equal to p1 plus p2. And then this propagator again is p1 plus k. And this is the momentum of the outgoing anti-quark. So the diagram below has the same structure, but for the lower leg. So the momentum of the gluon is still k. And the propagator going into it has momentum p2 plus k, but let's remember that is going in the opposite direction of the fermion line. So let me first write down what these expressions, just the expression for this amplitude, right? So let's do it carefully here, because we need to have all the elements of the picture. So let's start with the outgoing object, which is a U-bar spinor. And then we get to the gluon. The gluon is, let's say, the eyes are not so important, but I'm so used to write them, and then let me write them. So it has a GS coupling. It has a color attached to it. There is a matrix of color here, because this is the color object. Let me write it as TA. If I had to put color indices everywhere, this guy would have an A color index in the fundamental representation of SU3, and this would have an AB index, matrix indices, and the B will be the one of the outgoing spinors that we haven't written yet. Then I'm coming to the propagator, this propagator here. This is an I P1 slash plus K slash divided P1 plus K square. Then I'm coming to the IE of the quark, the charge of the quark, times gamma mu, which is the vertex of the photon, and then I'm done. Finally, I have the V of P2, which is the outgoing anti-quark, and this is the guy that has the index B. I'm being super specific right now, and then from now on, I will drop these indices because that's too much, right? So let's now take the soft limit of this expression, because that's why we wrote it down explicitly. So if I take and I have forgotten here, yes. So for the gluon here, we have there is a gamma matrix that is saturated on this one, so I've forgotten to write the epsilon. Let me make space for it, because I want to write that it is an epsilon of k. So it's IGS TA, and then here we have an epsilon slash of k. Now, so if I take the soft limit, what that means is just to the denominator that I have here, the same things that happened before happens here. So this guy here reduces to a 2p1.k. Now, in the numerator, I can neglect the k, because for the same reason as before, because it's a sum. It's a P1 plus k, it's not P1 dot k. So between P1 and k, P1 wins in the soft limit. So in the soft limit, this is the green is the soft limit. This goes away, right? And so what I'm left with in this expression is, apart from a bunch of prefactors, so I have a minus I, a GS, a EQ, and I can take the T matrix out as well. But as far as the spinors goes, is a U1 of P1, that is this guy here, and then I have epsilon slash P1 slash, which are these two terms here, and then I have sorry. Did I do anything? No, I'm confused. No. I'm confused about the gamma. The gamma mu, it was my... What is confusing me now? Because that is what was... okay, sorry. I have a moment of tiredness. Let me let me see what this is not working for me. This is all fine. No, it's all fine. So forget, it's all fine. So what I want to do here is just work with these two guys, because now if I write these as a minus P1 slash epsilon slash plus 2 P1 dot epsilon, just applying the commutation of the anti-commutation actually of the gamma matrices, then this P1 act on U bar of P1 and gives me 0. So this guy is 0, and the only leftover is that one. All good, because this expression now becomes, after this simplification, it becomes a prefactor. And then I have a 2 P1 dot epsilon divided 2 P1 dot k times the U bar P1 gamma mu that had to be there, V of P2. So the 2 simplifies. The TA, I can bring it back there if you really want. The EQ, I can also bring it back here if you really want. And the reason why you may really want, and even the I can come back here. So if, and the minus sign doesn't matter the moment in which I square things. So why I have reconstructed these is just because this is the original amplitude. This is the 0 amplitude. This is this object here. And so in the soft limit, that object becomes a power of GS times a prefactor times the 0 order, the one without the emission. The same happens here. So the same happens for this guy. Now, we are not going through the same calculation again. If you had to do it and reproduce exactly the same thing for the lower leg, what you would see is just that you get something that is the same kind of prefactor, but with a minus sign, and P2 instead of P1. And then you will get, again, U bar of P1, I, EQ, gamma mu, TA, V of P2. So again, this part here will be the one without the emission. So this is basically telling you that when you calculated the amplitude with the emission, in the soft limit, soft collinear limit, so in the limit that we were exploring before, you get a factor out of the amplitude without the emission. So in other words, it's telling you that the amplitude for gamma into Q bar plus gluon is equal to a prefactor that has, apart from maybe an I that is not really relevant for us, it's a GS, and then you would have the A amplitude for gamma to QQ bar times a factor that is the sum of these two objects. It's the sum of P1 dot epsilon divided P1 dot K minus P2 dot epsilon divided the P2 dot K, and that's it, right? So this is quite interesting because now what we can do is just to use this knowledge to calculate the sigma in this limit. And what we will see is just that it will factor out. So first of all, we see different things. So we see that the k dependence is all in here, in this limit. So if we now imagine to take this amplitude square and plug it back into the integration over the 2 to 3 phase space, the difference between the 2 to 2 and the 2 to 3 phase space is the d3k of the new particle, is the integration over the momentum of the gluon that we have here. But the two can factorize completely. The 2 to 2 and the 2 to and the extra gluon integration factorize because the k dependence is all here. So in other words, if you now let me take away the part, maybe I can take away something here. So let me take away this calculation, since you have seen the result. We want to keep the virtual part. And now that we have been able to simplify these in the soft and collinear limit, when we calculate the sigma real, which is the sigma for, in our case, if you want, will be the plus and minus 2q bar plus gluon, but we have calculated this as just gamma into it, plus gluon. This will be, let's look at what this will imply. It will imply a calculation over the phase space of the 2 to 3. Right, and the phase space of of an expression that is this one plus whatever we have neglected, because this is just extracting from the full mass of the 2 to 3 amplitude just the soft collinear limit of that. So if we extract this part here for the amplitude square, we will be a term that goes like alpha s, and then you would have the amplitude square for gamma to QQ bar. And then you would have this factor, which is the P1 dot epsilon divided P1 dot K minus P2 dot epsilon divided P2 dot K square, right? And then on top of this, there is everything else that is not soft and not collinear, where the soft and collinear refer to the K, refer to the gluon, right? So this part here, this part is the part that we don't want to calculate, because this part is indeed the important one, because it's finite, but it's not something that we calculate by hand. So leave it aside, it's not problematic, it's not our point right now. This part is the part that we want to have under control, because we hope that out of here we get the divergent terms that will compensate the one that we have on the other side. And the leftover will tell us something about the shape of the radiation. That's where we are going. So if I look at this part, the phase space measure here is made of the phase space of the 2 to 2 times the d3k over 2 pi cube 2 omega k of the gluon. This is the phase space of the gluon. Right? But the k amplitude is all here. And the integral over dps 2 to 2 will pick up only the part that is already the sigma QQ bar. So it's a one without the emission. So we are going to get a factor that comes from the integration over d3k of this part here, multiplied by the cross-section of the object without the emission. So if I have to, let's look at what this square is to start with. This is a form that is very simple, because when you take the square of this object, for massless objects, you have two terms that are P1 square and P2 square that are 0. And you have a term, of course, here you have to sum over the polarization. So implicit in this square, there is a sum of epsilon nu. And here you will get a minus g mu nu, plus terms, if you use some different convention, that will go to 0 saturated with the P1 and the P2, or the K. So the net result of this square, as you can easily calculate, is this one. So the object that we want then to control is the d3k over 2 pi cube 2 omega k times that thing, 2p1 dot p2 divided p1 dot k, p2 dot k. And we know that it has an alpha s out in front. So if you work out this integration a little bit, so what these, one thing that I have forgotten to do, however, here, is the fact that I've been a little bit sloppy, and now I've erased the things that I had that I have in there, in bringing along not only the GS but also the TA matrix, because now when I square things, the TA gives me a factor of a color factor, and is a color factor that comes from the sum of TA. So this object here is something that will give me a CF color factor in front of the F that is coming from the sum of TA. And this is CF, which is n squared minus 1 divided to n, with n equal 3 if it's SU3. So this object will have a CF out in front as well, and you will have, to start with, a GS square. So when I put everything together, let's elaborate more on this d3k. This d3k will have an omega k squared d omega k, a d cosine theta, and a d phi. Now, if I have all the factors that I need, so this object here, remember that you're working in the center of mass. So this 2p1 dot p2 is a 2e1e2 times 1 plus the cosine theta of the two objects when theta is back to back. So this object here gives you, I put it in parentheses, a 4e1e2. And downstairs in the denominator, you have a e1, e2 omega k squared times 1 plus cosine theta from one guy, and 1 minus cosine theta for the other guy, for the same reason that the P1 are back-to-back in the center of mass. So the E1 E2 cancel. And now, modulus having got all the factor of 2 rights that I invite you to check. So what is coming out of here should be an alpha S, which is a GS over 4 pi that I get from here, a CF, a factor of pi that is left over here because I have 2 pi cube that are left here. And then I have a d omega k that comes here. I have an omega k squared and an omega k squared, but one is left. I have a d cosine theta divided 1 minus cosine squared theta that are the products of these two, that therefore I can write as a sine squared theta. And this guy in the limit of small angles becomes a d theta over theta. I left you to do that. And then I have a d phi with the leftover pi that come from here, and even a factor of 2. And I think that at the end, because of these 4 that I have here, and this is a factor of 8, I have 2 far, but then I have another 2. So I think there is an extra factor of 2 up here. You check this expression. But in any case, apart from the factor of 2 that is not particularly interesting, this is the form of the factor that is coming out from the integration of the gluon part of the story. So this is the gluon contribution in the soft region to the sigma real. So what the sigma real now is, out of having calculating the integral, there we wrote it in green, so let me write it in green here too. the sigma real now will be equal to this structure integrated over omega k and over omega k and d theta, so integrating over d omega k and d theta. So let me replace these so that I get it out of my way here. This is a d theta over theta. So in that calculation, in the soft limit, which is this first part, not the finite one, this first part reduced to the integration over this factor. So the sigma real becomes the integration over this factor that has the same, if you notice, the same double singularity that we had over here. So you see what I have outlined here. If you notice, that's exactly the same structure that we have over here. The integration over d4 pi is 1, because it's d phi over 2 pi, so the phi, there is no dependence on phi, so this goes away. And this has this prefactor that when you calculate the things carefully, will coincide exactly with, of course, the order of alpha s, but also the C1 and the C2 that you have over there once you do the integration, that, as you see, has both a double singularity and a single singularity, the moment in which you keep only one singular and the other not. So once you do this, when you complete the calculation till the end, what you're going to get is just that this guy will be, again, the sigma 0, which is the part that corresponds to the square amplitude of the QQ bar production, integrated over the part of the phase space, this part here, integrated over the part of the phase space that does not involve the gluon. It is of order alpha s. And once you have completed the integration over d omega k and dtk of this factor that I have here, you will see that what comes in here is exactly minus C1 over epsilon IR square minus C2 over epsilon IR. So this is the soft collinear part, and then you have sigma real finite. So your homework, if you want, will be to figuring out the C1 and C2 in the integration of sigma virtual, and figuring out the corresponding to coefficient on the soft part, of which I've given you all the elements, because the integration is exactly this one. And I told you what it looks like, so you can just do this integration. It takes 2 seconds to do it, the same on the other side, and verify that the only difference between your two calculations that are one line of calculation is a sign. It's the only difference. And that sign is exactly what cancels this part of the infrared story with this part of the infrared story. So your cross-section is infrared finite, modulus having introduced both terms. What do we learn from here in terms of the shape? So what we learn from here in terms of the shape of the radiation is just that the divergences have canceled. But as we all know, whenever these whenever divergences of this kind, so which kind of divergences were there? These are logarithmic divergences, right? You see it here. So what is left over in the finite terms after the integration will be logarithmic corrections that are large, both in the case of the virtual part, but in particular in the case of the radiation. So what this is telling us is just once we have done all this nice work, and we are so happy in seeing that our intuition of the fact that the radiation in certain limits will have to merge into the n-1 process. So we'll have to merge into the process that doesn't contain the radiation. But there are leftovers to that. And the leftover to that is just there are logarithms of the angle or of the energy that enhance the soft collinear limit. The soft collinear regions. So what this is telling us is just that whenever you have, it's telling us something about the shape of the radiation, because the finite terms that are left over after their integration, apart from terms that are completely innocuous, there will be large terms of logarithmic nature that will favor, in a way, the phase space that is either close to the hard original patterns, so the collinear region, not divergent, but still at small angle with respect to the direction of the original pattern, and at small energy with respect to the energy of the original pattern. The one at small energy is just some soft stuff that is around the direction of the original patterns. The one at small angle is really what shapes the radiation of QCD. So coming out of this hard scattering, there will be hard partons that are our Q and Q bar of that calculation, and they will emit preferentially over and over at an angle that is closer to the direction of the original parton. Not because there is nothing else, but because that region is favored. So the integration over phase space is sort of flat, if not for the fact that the matrix element is peaked in certain regions. So it's peaked in the collinear and soft region of the problem. So this is telling us, just from a simple calculation in QCD, from a first-order calculation in QCD, based on just the form of the Lagrangian of QCD, of any non-abelian theory like QCD, as a matter of fact, that if these are the original parton coming out of the radiation, so coming out of the process, they will emit, and that's why I drew them kind of close to where they will keep emitting close to themselves. So in a sort of regions that naturally creates these sort of jetty shapes that are exactly the shapes of jets of QCD, which is exactly why we define not also being able to see the individual partons, but why do we see jets is exactly because of this, is exactly because of that. So this is also the principle on which parton showers are based. So parton showers, as we will, now we don't have time, but as we will see probably briefly as first thing tomorrow, are just based on the calculation that we did today. So they're based on really seeing that the emission of the emission of radiation from a hard parton is weighted by this kind of factor. And we could do exactly the same calculation when the hard parton was a gluon. The only difference that you will see is just that this CF color factor become a CA. That's the only difference. And then the kind of radiation factor is exactly the same. Knowing this, you know the probability of emission of a gluon from a quark or a gluon from a gluon, and you build your parton shower just by ordering in energy or angle your emission and assigning to each branching every time there is an emission a probability. That is exactly the one that we have calculated today. So this is the really bread and butter of parton showers. There is nothing else into it. And that's why they evolve, that's how, not why, but how they evolve the radiation of QCD from the hard scattering to lower and lower energies. And we'll comment tomorrow about is that what we should do? Is that good enough? Is not good enough? And etc.
Thank you, Laura. And questions for Laura? Yes.
Thank you for the talk. And I was just wondering, the first time that you said, oh, there's a virtual and the real contribution, I immediately remember of the optical theorem. And I was thinking, what if we could predict that we could solve this problem before even considering the real by, I don't know, looking at the virtual one and cutting and seeing that it looks like the real part?
Well, you could calculate an amplitude square using the optical theorem. That's right. That's actually a way in which certain calculation of real emission have been done just by calculating the imaginary part of the 1 to n, right, or 2 to n, right? So that's, but it's just a method of calculating it. You would see the same, right? Yes, you can use it, but you would see the kind of same compass. In the optical theorem, you would have both contribution within the bubble of the optical theorem, and you would just see the same.
Okay, perfect. And just a quick question, just to confirm that I understood, this small angle, this jet forming, is it because we have this IR divergence in the angle, and the small angle region is the one that has the most impact because of the hadronization.
Because of the shape of the integration, right? So when you in that limit, in the soft collinear limit, the integration measure goes in energy and angle is really of logarithmic kind. So the divergence is a logarithmic divergence. If you imagine, so if you regularize that by in dimensional regularization as we did, you would get the divergence as 0 in the logarithm as a pole. But there is a leftover to that. So the integral is not just that because you have boundaries. So the leftover of that integral is a log. It has a log shape, right? And so that's why we talk about the logarithmic enhancement, because it's the logarithmic enhancement that when the scale of energies are small on one side, not 0, because that we have extracted with the divergence to whatever other scale, it's a largish log, right?
That's real nice. Thank you.
More questions for Laura? Yes. Can you pass the mic?
Okay, maybe my question is super trivial, but I have
No
few
question
steps
is
that
trivial in
I
these
couldn't
things.
follow. At first, you're using every time P1 and P2 square equals 0, but
It's a 4 momentum. Right, but we take them massless. Yes, yes.
and I
Yes,
guess the reason is the same.
Of course, yes. So light quarks, you normally take them massless, right? If these had to be, let's say, a bottom quark,
Yeah.
unless I'm really at high energy, I would probably not take it massless.
Yeah.
And then the difference, there is not much difference actually. The difference between, it just gets a little bit more complicated, longish, right, I would say. That's why I didn't do it. So for instance, in here, right, everything else stays the same. But, well, except that here you would have denominators with masses, right?
Yeah.
But remember, so it's not much difference. So when you do P1 plus K square, you, instead of this one, for a massive quark, you would have P1 plus K square minus the mass of the quark square in your propagator. So, but now P1 square canceled that. So at the end of the day, it's still 2P1 dot K plus K square, right? So this doesn't change. And here, what you would get is just that when I, the interference between P1, so when I multiply P1 dot epsilon star times P1 dot epsilon, I get a P1 square there too. So I get a term that is M squared divided P1 dot K squared. So I get an extra piece of soft and collinear divergences. But I get it both in the virtual and in the real. So they still cancel, right? Yeah.
Okay, my next question is related with this equality that you have over there with the cross-section real. Because you're saying, basically what you say is that you can separate the amplitude into the amplitude at 3 level and this prefactor. But this is not completely true because of this generator of SU3 that is mixing quarks. So somehow there is some difference there, right?
No, it is true. It is true. So when you square it, it is true, right? Because so you see this amplitude here doesn't have any color matrix in it, but these objects are colored. So when I square it, I get a trace of 1, which is n. So this has a factor of a color factor of trace of 1, 3 by 3 matrix of SU3, which is n. The other one has a trace of TA. So here I just wrote it this way, but what you actually have is this thing here, which is CF times the trace of 1, which is n again. So this n goes into here because it belongs to there, and the CF stays out. So the color works, right?
Yeah, exactly. It's just when you take trace, you have like 2 generators at the end. You have this delta, no, that make it to the diagonal of the color, I guess.
Yeah.
Okay. And also, last question is at the end you have these infrared divergences that are solved this way, but you have also the finite pieces that I guess you have to compute. You have to compute both, right? The real and the virtual.
Yeah. It's just that for our discussion here, I only needed the dominant part, the dominant from the point of view of what dominates the integration over phase space, which is this part here, and shapes of course, you have things. It's not that you see things only at a super collinear region. You have a kind of a broadening of the cone, right? And depending on the energy scales, this is or the boosting of your collision. This has different shapes. But the trend is really to concentrate the radiation closer to the emitter, right?
Okay, that's it. Thanks. That's all. Thank you.
Okay. I wanted to ask about in the beginning, right? The length. What is the length scale of how long do the parton showers occur? I mean, is it comparable to the size of the detector so that you can observe the showers before they hadronize?
Uh, yes, yes. So these things I mean, we have not talked about the actual shape of a detector, right? You can see that I'm not really an experimentalist, otherwise I should have said it in day number one, right? But yes, the detectors have this onion shape in which they have different kind of layers that detect the different things, and at the end they have an hadronic, what they call an hadronic calorimeter, which is the last one. And the detector is engineered in such a way to take in everything that is produced. And honestly, the scale of hadronization is not large, right? So the energy is deposited on a reasonable scale of the size of the detector in such a way that the energy goes below, gets to the 100 MeV scale, which is the scale of lambda QCD, within that length, right? And so you produce a hadron, so quite soon, right?
Okay, so we actually can detect like the parton showers, their tracks, like this length is in like microscopic or like.
You see just a spray of hadrons basically coming out already. We don't see isolated quarks, so that they hadronize pretty quickly, right?
Okay.
Yes.
Yeah, just a real quick one, please. If I recall well, the result that you presented here is the first step of the KLM theorem, right?
Mm-hmm. Yeah, it is
no.
yes.
Right.
Yes.
And now I cannot recall well whether this holds order by order in alpha expansion. It should hold, right? If you, for example,
by
do
order
the
for inclusive quantities.
for the inclusive quantities, right?
inclusive,
So if
this is
you,
a
for
comment.
example,
Yeah, we'll have a series of comments that we will have to make tomorrow when we start when we
Right.
have our lecture
So
tomorrow,
it's-
and one is this
it's
one.
very powerful in
Yes,
the end. Thank
yes.
you.
Any other questions? Yes.
So were these calculations made for alpha fixed, right?
For alpha,
Alpha fixed?
at order alpha.
Okay. What is expected when we have the running coupling constant?
Okay. No, I mean, I see what you're saying. So technically, it's not for fixed alpha. Alpha is a function of the scale, and actually is what allowed us to say here we are perturbative, here we are not perturbative anymore, right? So I haven't specified here what is the scale of alpha because it was not so important for our discussion beyond the fact that we are at high energy, so we are perturbative, right? So beyond that, we will kind of mention it more. So the scale of alpha is the scale of normalization. Or it's a scale of that then can be fixed to be the scale of the center of mass of the process or whatever else, right? We will get a little bit more into how relevant that is when we'll discuss the kind of systematic error that we have in using a scale as opposed to another one.
Okay.
And we'll discuss that.
Okay, thanks.
But you have to, whenever you see alpha, it's alpha S of a scale, right? Right.
Okay. So let's thank Laura again.
Yeah.
Not easy. Huh?
To stay in the right time.